All right, so in 8.4, we talked about finding the coefficient, expanding it, finding Pascal's triangle, and finding a single term within the expansion, which this warm-up covers. So the first one is just finding the coefficient. So this is where you need to know the formula. The CNR would be n factorial over n minus r factorial times r factorial. So this would be 8 factorial over 8 minus 3 factorial times 3 factorial. 8 times 7 times 6 times 5 factorial over 5 factorial times 3 times 2 times 1. 5's cancel. 2 goes into 6 3 times. 3 cancels with 3, and I should end up with just 56. Good so far? Yes? Okay. Second one says write the expansion of the expression. So the first thing you want to identify from your initial binomial is how many terms there should be in your answer, which is what? There should be 4. So if n is 3, which is my exponent, then there should be 4 terms in my expanded binomial. So then I do the first one. I take that first term and I raise it to the highest exponent, which is 3, and then work my way down to 1, 0, and then go the other way with the second term, which is negative 3y. Negative 3y to the 0, negative 3y to the first, negative 3y to the second, and negative 3y to the third. And then I'm going to simplify that out. So this is 8x to the third. This cancels out. This is 4x times negative 3y, which is negative 12xy. This is 2x times 9y squared, or 18xy squared. This cancels out. This is negative 27y to the third. So far I am there. 8x to the third is going to get multiplied by something. The negative 12xy is going to multiply by something. The 18xy squared is going to get multiplied by something. And the negative 27y to the third is also going to get multiplied by its coefficient. Yep.
Isn't it negative 12x squared?
X squared. Yes, thank you. This should be squared. Okay, so now I got to figure out my coefficients, and there's 2 ways I can either use Pascal's triangle, which I'll see in a second, or I can do my individual coefficients, where the number's on the left, the n is on the left, which we said this is raised to the third power, and I work my way up from 0 to 3. So I'd be C3, 0, C3, 1, C3, 2, and C3, 3. Okay, because we've done this a couple of times, we should know this is a 1 and this is a 1. The in-betweens are 3s. So if you don't know, you need to work it out, but obviously you can start memorizing those because they don't change. There's 4 terms, it's always those 4. So this is 1, this is 3, this is 3, this is 1. And then from there I multiply them out. So 1 times 8 is 8x to the third. 3 times negative 12xy is a minus 36x squared. Oh, that should be squared too. Y. 18 times 3 is positive 54xy squared. And 1 times negative 27y to the third is negative 27y to the third. And there's your expanded binomial. Questions on that one? All right, number 3, write the first 6 rows of Pascal's triangle. So this would be row 0, but it is technically the first row. It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, which is the one we just used. 1, 4, 6, 4, 1, 1, 5. Wait, that's 0, 1, 2, 3, 4, 5. 10, 10, 5, 1. There's my 6 rows of the Pascal's triangle. So remember that this would mean that this n is 0, n is 1, n is 2, n is 3, n is 4, n is 5. So I'm actually going to add to it so I can use Pascal's triangle for the next one. But that is all you needed for that question. So I'm going to do 1, 6, 15, 20, 15, 6, 1. That would be if n is 6. The n here is 7, so I'm going to go one more. 1, 7, 21, 35, 35, 21, 7, 1. So this is the row I'll use for the coefficients of the next question. So it says find the sixth term of 3a plus b to the seventh. First thing we want to identify is n is 7. Second thing we want to identify is what's r. So if it's the sixth term, what is r? 5. Always one less. So I'm going to raise the first, well, first I'll do the coefficient. So coefficient 7, 5. And then I'm going to raise that first term, which is 3a, to the n minus r. And then I'm going to raise b to the r. So if I'm using row where n is 7, it's technically the 8th row. This would be the term that is 0. This would be 1. This would be 2. This would be 3. This would be 4. This would be 5. So the coefficient I want to use is 21. N minus r would be 7 minus 5. So that would be 3a to the second, which is 9a squared. And then r here is 5. So this is b to the 5th. And then multiply it out, and I get 189a squared b to the 5th. So if it asks you for the individual term, and I don't care if you use the coefficients, if you use Pascal's triangle, that's totally up to you. Be prepared to do something like that without a calculator. Okay? So there's going to be, like I said, 2 parts. Something like that would be without. So you won't be able to use the calculator to find the coefficient. Just make sure you know how to do it. Questions on any of the warm-up? So 8.5 is called counting principles. This is baby stepping our way into more probability. Okay, so today we're going to learn how to build how many, like the number of terms in a sample set, basically. And then we'll finish this tomorrow. But 8.6 is then finding the probability that events will occur once you know that set. So there's something called the simple counting problems. This is where I could ask you, there's 10 black socks in a drawer and 5 red socks. What's the probability you'll pull a red sock? Something that's simple, easy to count, right? I would just figure out how many red socks there are over the total amount, that kind of thing. So if this says find that, or what's the probability you're going to pick an even number between the numbers 1 to 10. You can, I don't even know why I put the 4 to 8. That doesn't make any sense to me. Ignore that. So the numbers 1 to 10 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which of these are even? 2, 4, 6, 8, 10. How many of them are there? 5. So if I ask you what are the odds, or what's the probability of picking an even number, you would put 5 over 10. So the odds are 1/2, like flipping a coin, okay? They call them simple counting problems for a reason. So these don't require any formulas. There's nothing you have to figure out, okay? It's basic, like common logic in the beginning. And then obviously it changes. So there's 2 things you need to start to look for, which is replacement and without replacement. If something has replacement, it means you begin with a fresh set every time. So for example, yesterday when I walked around with that mug and you pulled out numbers, let's say, right? If there was 34 numbers, when you walked through the door, how many possibilities were there for you to pull if you were the first person? 34. If I said, okay, put it back, and the second person walks in, how many possibilities are them? 34. That's with replacement. If it was like it actually happened where you pulled a number out and you kept it, now person number 2 comes, and how many do they have? 33. And then the next person would come, 32. That's without replacement. So you want to pay attention to things like putting back or replacing, okay? Because that will determine if the next time around you're starting with a fresh set or an altered one. So this one says, determine the number of ways in which a computer can randomly generate one or more such integers or pairs of integers from 1 through 15. So your sample set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So how many different ways can an odd integer be picked? How many odd integers are there? 1, 2, 3, 4, 5, 6, 7, 8. how many ways can an integer that's divisible by 4 be picked? So what's divisible by 4? Is 4 divisible by 4? Yes. What would be the next? 8. Then? Any more? So how many ways can you pick? 3. So again, we're just establishing this sample set now. You're not saying what's the probability that you'll pick that number. Then it would be 3 over 15. But for now, we're just saying what is. Example 2 says 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box. Its number is written down and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box and its number is written down. Finally, the two numbers are added together. In how many different ways can a sum of 12 be obtained? So if I have 1, 2, 3, 4, 5, 6, 7, 8. And somebody reaches into the bag and pulls 2 numbers out. What 2 numbers are going to result in a sum that's 12? 4 and 8. So if they pull first the 4 and then the 8, that's one way that 12 can be obtained, right? What's another way that 12 can be obtained? 5 and 7. So first they pull the 5, then they pull the 7. What else? 6 and 6. So the numbers return to the box, right? So I grab 6, but I put it back. I pull another number, and it can be 6. No, it says how many different ways. So not how many different pairs, how many different ways can it be pulled. So if I first pull out an 8 and I pull out a 4, am I reaching 12? And is it a different way than pulling out 4 and then pulling out 8? Yes. So that means you can also do 8 and 4 and 7 and 5. 6 and 6 and 6 and 6 reverse is the same, right? It's not like these are numbered, like colored pieces of paper that you would know the difference, right? That's the same piece of paper. So how many ways can the sum of 12 be obtained? 5. Questions on that one? Example 3. Almost exactly the same thing except for what? The paper is not returned. How does that have an impact on what we just found? You can't get 6 and 6, which means you can get 8 and 4, 4 and 8, 5 and 7, 7 and 5. But you can't get 6 and 6, which means this time there's only 4 options. Questions so far? Everybody okay? All right, the fundamental counting principle says if you have 2 events, and we'll call them E1 and E2, so 2 separate events, and the first, and this should be a T, and the first event can occur M1 different ways, and then after E1 has occurred, E2 can occur M2 different ways. The number of ways that the 2 events can occur is M1 times M2. So if you're doing 2 different things, you would take the amount of times the first one can happen times the amount of times the second one would happen. So how many different pairs from the English alphabet are possible? 2 separate events. Pulling the first letter, pulling the second letter. When you're grabbing a letter from the English alphabet, how many possibilities are there? 26. Now that event is finished. Second event comes into play. You're grabbing a letter from the English alphabet. How many letters are there? 26. So they're 2 separate events pulling from the same English alphabet. So I would say that this is different. You would pay attention to something if it said, the English alphabet is written on pieces of paper or on cards. And the first event occurs, you take it, and you want to pay attention. Is there replacement or is there non-replacement? If there's a replacement, then it's 26 again. If there's non-replacement, that's when it comes to 25. So that's when that second event relies upon what happened in the first. Does that make sense? But a set of numbers from a random computer is going to be always the same set of numbers. The set of letters from an English alphabet is always the same, okay? So you're gonna, the hardest part to teach you on probability and all this stuff is how to read the questions because they are so different. I can't tell you exactly what to look for. You wanna look for things like replacement and non-replacement, that kind of stuff. But in general, a lot of it takes your interpretation of the words. So what's 26 times 26? Is that right? No, right?
Yeah.
Say again? No, 576, right?
Yeah.
676. 676. Took me longer to walk over here than it did to actually multiply that out. Okay. Example 5 says a combination lock will open when the right choice of 3 numbers from 1 to 30 inclusive is selected. How many different lock combinations are possible? So there's a couple of vocab terms you want to pay attention in there. What does inclusive mean? Including 1 and 30. So how many numbers are from 1 to 30 including 1 and 30? 30. Remember, if we start at 1, it is that number, okay? So there's 3 numbers. I've got my first number, I've got my second number, I've got my third number. How many options are there for the first number?
30.
How many options are there for the second number? How many options are there for the last number? So something that said numbers couldn't repeat, then it would change, okay? But you're saying you're pulling from the same set of 30 numbers every time. So this would be 27,000 combinations. All right, this one says, in a certain state, each license plate number consists of 2 letters following by a 4-digit number. How many distinct license plate numbers can be formed? All right, so I've got 2 letters. First one is a letter A through Z. The next one is a letter A through Z. And then a 4-digit number. How many letters are there in A through Z? 26, which means there's 26 to pull from the first time. Does it say a letter can't repeat? No. So how many letters are there the second time? 26. And then I need a 4-digit number. What does that tell you about those individual numbers?
Up to 9.
They go only from what to 9? What else is a 1-digit number? 0. They go from 0 to 9. How many numbers is that? 10. So you get 10 and 10 and 10 and 10. So this was 676 and 1, 2, 3, 4 zeros. So next time you drive in your car, you could be like, Mom, did you know that there's 6,760,000? No, just kidding. The things you think you won't use every day. Question so far? All right, permutations are next. So a permutation is determining the number of ways that n elements can be arranged in an order. So this is where order matters. Let's say I want to give you guys new seats and I want to figure them out and I want to know how many possibilities are there to rearrange you guys in order. So I've got 34 seats and this first seat, how many people can, let's say there's 34 of you. How many options do I have to fill this first seat? 34. And then I go to the next seat. Now this person's already sitting, so how many options do I have now? 33. How many options do I have now? 32. So those are each individual events, yes? To figure out what the options are, I would multiply those events out. So it would be something like 34 times 33 times 32 times 31 and so on and so forth. What does that look like? A factorial. So permutations are factorials of the number that you're trying to fill. This is where order matters. So you're going to look for words like order. Order matters. How many ways can 10 people get into a bus? How many in order? How many ways can people finish in a finish line in a certain order? How many times can it, and it will literally say order matters. And that's how you know to do permutations, okay? So how many ways can 10 objects be put in order would be what? So without a calculator, you are multiplying 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If your teacher says to bring a scientific calculator and you don't bring one, oh, it's going to be fun. Okay? What you want to start doing is get comfortable with that scientific calculator. So if you have one with you, you can take it out because most of them have that factorial sign. You just got to find it. They're in different places depending on that calculator. Find the number of permutations of the following letters. A, B, C, D, E, and F.
Is the whole test going to use scientific?
Mm-hmm. How many letters are there? 6. So it is 6 factorial, which is 720. So these are questions that standardized tests love, again, because you could rewrite out ABC, ABD, ABE, ABF, then go ACD, ACE, ACF. You could figure it out. It just takes you a crap ton of time. You shouldn't need to if you know something like this. Okay? Questions on that one. So this is permutations, order matters, so you can't like switch it around. You're not going to count A, B, C, and C, B, A, that kind of thing. Once you use it, it's used. All right, this is where we're going to do this, and then we're going to stop for today. So permutation of elements taken at a time. So let's say I went back to that last example, and I said, find the number of permutations from that set of letters taken 2 at a time. That's when your equation changes. So it looks just like your coefficient one, where the n is on the left. That's the number of items that are in that set. The r is how many you're taking at a time. And the equation looks almost exactly like your coefficient one, right? What's different? There's no r factorial on the bottom. So it's n factorial over n minus r factorial. So I'll tell you right now that on your test, if it's a question like this, let's just say, or even a coefficient one, that I'm going to let you use your scientific calculator, but you are going to give me the formula first. So it is a show all your work kind of a scenario. What would that look like? If you want to use your calculator, use your calculator, because some of them have the permutations and some of them have the combinations on them. So a question would look something like A. Find the number of permutations of 8 horses taken 3 at a time. So what's my n?
6.
Oh, no. Number, the whole number for A. 8 horses, right? How many are you taking at a time? 3, that's your R. My formula is n factorial over n minus r factorial. So it's 8 over 8 minus 3, which is 8 over 5, and 8 times 7 times 6 times 5 factorial over 5 factorial becomes 8 times 7 times 6. Which is 336. And then really obvious, evaluate 6P2. So find on your calculator if you have a probability button, or some of you actually above your button, I think that's yours, Karina, like says NPR. That's where you would use it. Most of them you have to type the N first, then hit the NPR button, and then hit the R. So it would be 6, NPR, 2, and you get 30. So 6 factorial over 6 minus 2 factorial, which is 4 factorial, equals 6 times 5 times 4 factorial over 4 factorial. 6 times 5 is 30. Questions on anything we talked about today? So 8, obviously 8, 4. So your test is going to go all the way to 8, 6. Okay, so we've done expanding the binomials, figuring out the coefficients, and then the coefficients is actually going to come back in this section as well when we finish it. But then we got into simple counting and permutations. So distinguishable permutations basically come into play when part of your set is repeated, whether it's a letter or a number or an object in which it occurs more than one time. So if I were to say pull 3 letters out of the alphabet and somebody pulled A, B, C, that's one set of numbers that could come out. And then somebody else, we start over again and somebody else pulls B, C, A. Is it the same set of numbers? Letters. Same set of letters. Thank you. Yes, right? A, B, C, B, C, A. The order there doesn't matter. It's the same set of letters. So if a value repeats, you have to accommodate for it. So if in this one says, suppose a set of n objects has n1 of one kind of object, n2 of a second kind, n3 of a third kind. So if I had 3 A's, 4 B's, 5 C's, then you would count how many there are. Those would be your n's. And the number of distinguishable permutations of the n objects would be given by n factorial over n sub 1 factorial, n sub 2 factorial, and so on and so forth until you've accounted for all the objects that are in the bag. So if I had a bag of 10 red socks, 5 black socks, and 7 purple socks, and I asked you to pull out 3, how many ways can you get each one? You would have to account for the repeated one. So oftentimes this is the result of like a letter, of a word. So you'll see a word with repeated letters, and it will ask you to find how many distinguishable ways the letters can be written. So this is where you want to account for each repeated one. So what are the different letters that you see in the word banana? What are they? B, A, and N, right? How many times does B occur? Once. How many times does A occur? 3 times. How many times does N occur? Twice. How many letters are there in total in that word? 6. So that's your N. So I get 6 factorial over 1 factorial times 3 factorial times 2 factorial. 6 times 5 times 4 times 3 factorial over 1 times 3 factorial times 2 times 1. The 3 factorials cancel out. 2 goes into 4 twice. So you get 6 times 5, which is 30, times 2, which is 60. Questions on that one? Okay, the last part in the section is based on combination. So combination versus permutation. Permutation order matters. Order being A, B, C would be different from B, C, A in a permutation. In a combination, those 3 letters are accounted for once, no matter what order they're given in. So this should say letters. Okay. So the combination is selecting a subset, so a specific amount of items from a larger set in which the order is not important. It doesn't matter if I pull red, then green, then blue, or green, then red, then blue. My set involves 1 red, 1 green, 1 blue. I only count it once, okay? So in this case, it would be something like, how many ways can letters be taken from the alphabet 3 at a time? So if I pull A, B, C, it's the same. I count it once instead of counting A, B, C once, B, C, A once, C, A, B once. Those would all just be one option. The equation is this, and hopefully this looks familiar. What do we use that for? To find the coefficient. So it's the same formula. So the N is the number of objects that would be in your entire set. The R is how many you're taking at a time. And then you just plug it into N factorial over N minus R factorial times R factorial. I'm actually going to go back. Hang on. So if you go back to what was on that last slide, which said how many ways, this should have been, can letters be taken from the alphabet 3 at a time? So how many letters are in the alphabet? 26, that's my numerator. And then if they're taken 3 at a time, what's my R? 3. So this would be 26 minus 3 factorial times 3 factorial. So I'd get 26 times 25 times 24 times 23 factorial over 23 factorial times 3 times 2 times 1. 23's cancel. 2 goes into 24 12 times. 3 goes into 12 4 times. And then I would do 25 times 4, which is 100, times 26, 260. Questions on that one? So if I go, all right, so example 10 says, in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? And the order of the elements is not important. So again, that's how we distinguish the difference between combination and permutation. This is obviously what? Combination. So what is my N? How many letters are in the set of letters I'm pulling from? 5, right? A, B, C, D, and E. 5. And how many am I pulling at a time? 3. So I'd get 5 factorial over 5 minus 3 factorial times 3 factorial. And then I get 10. So right now I have your test divided into 2 parts, with a calculator, without a calculator. Something like that would be fair game without a calculator. I'm hoping you can multiply something like 5 times 2 without a calculator. If this was larger, like you'll see in the next one, it would go on the second part in which you're using a calculator. However, it will say make sure you show your work, meaning give me the formula and then give me your answer. Some of your calculators have the NPR button and the NCR button, and some of them don't. So I'm trying to level out the playing field, okay? It doesn't mean you can't use that button to check it. That's fine. If I give you the calculator, you can utilize it as much as you want. It's just you're going to have to give me at least the formula behind it. So a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? And order is not important, which again means combination. So what is N this time? 52. And that's an important thing to remember, especially when we get into the next next section. There are 52 cards in a standard deck of cards. How many are we taking at a time? 5. So 52 factorial over 52 minus 5 factorial over 5 times 5 factorial. 52, 51, 50, 49, 48, 47 factorial, 47 factorial, 5 times 4 times 3 times 2 times 1. So the 47s cancel out. I can go 2 into 48, 24 times, 3 into 24, 8 times, 4 into 8, 2 times, and 5 goes into 50, 10 times. So I just have to multiply out 52 times 51 times 10 times 49 times 2. And I get 2,598,960. So let's say you're given the same piece of information and one problem says order is important and one problem says order is not important. So one's a permutation and one's a combination. Which one do you think there's going to be more of? Are there more permutations or there's more combinations? Permutations, okay? If we compare just if you think about it, so this is saying A, B, C would count for a permutation, so would B, C, A, so would C, A, C, B, A. So it's literally 3 times the combinations if it's 3, okay? But if you just even look at the equations, so for permutations, it's n factorial over n minus r factorial. And for combination, it's n factorial over n minus r factorial times r factorial. So for combination, I'm dividing by an extra number, which makes it smaller, okay? So if you were to just look at those equations, those should be different. So there are more permutations than there are combinations, because in something like 2 letters from an alphabet, A, B counts, and so does B, A for a permutation, but it does only counts as 1 for a combination. Questions overall on anything 8-5 related?